Okay, so last time we talked about one of the first models of atomic structure called the Bohr model. We applied it to hydrogen and other one-electron systems, and we saw that we could use this model and the associated equation to predict energy levels and to predict atomic transitions, which involve either absorption or emission of photon energy. But as is often the case with some of the earlier and simpler models that explain chemical phenomena, there are some problems with the Bohr model. And the biggest issue is what happens when you try to apply the Bohr model to multi-electron atoms or multi-electron ions, as it were. So anything that has more than one electron, the Bohr model just simply doesn't work. So we saw that the value of the Bohr model was predicting energy levels, and it just, when you have more than one electron, the Bohr model fails to predict energy levels. Now, as we'll talk about, energy levels for multi-electron systems are more complex because now you also have not only the interaction of the electron with the nucleus, but you have interaction of electrons with each other. So that's part of the issue, but no matter how they tried to refine the Bohr model, it just didn't work for multi-electron systems. So one thing that they tried to try to refine the model is, well, what about elliptical orbits? So we talked about in the Bohr model that the electron is moving in a perfect circle around the nucleus, and they said, well, what if it's not a perfect circle? What if it's an ellipse, some sort of elongated orbit? So they adapted the model to account for this, and it, this was one idea that came out. And so people worked on this and came up with new equations and tested the model on real systems. So people adapted the model to include elliptical orbits instead of just purely circular ones. And this was a great idea, but like many ideas, it didn't pan out, so this didn't work either. So that's the short story there. So you can try to improve the Bohr model in this way, and it doesn't improve things. So this is kind of how it goes in science. We talked about the scientific method on the first day, and you develop a model, you test it, you refine it, and sometimes certain ideas that you have don't work out and don't they fail to predict the physical reality. So the bottom line, the reality is that the Bohr model only works for one-electron systems. So we talked that hydrogen is the only neutral atom that it works for, but you can have ions that only have a single electron where it works just fine. So the Bohr model only predicts energy levels for one-electron systems. So don't try to use the Bohr model for any other situation. Is the bottom line there. And then the other limitation of the Bohr model, even though the equation works very well for one-electron systems and is entirely accurate as far as we can tell, the physical reality is that electrons do not move in circular orbits. So that is an oversimplification of electronic structure. And that's an idea. We want to appreciate the significance of that idea and how it was really the first attempt to explain atomic structure in any level of detail, but it's simply just not true. So these circular orbits that we talked about, this planetary model that the Bohr model lays out is just not the physical reality at all. Okay, so now we have to think about how do we describe multi-electron systems? And before we go into the details of that, we need to come back a little bit to some more fundamental ideas of quantum mechanics. So this Schrodinger equation that you've presumably heard of in some context is really what we're going to use to describe electronic structure. So the equation looks like this. You have h with a little hat on it times another Greek letter psi is equal to the energy E times the wave function psi. Now I'm not going to write out the Schrodinger equation in any detail. Now the point is the Schrodinger equation can apply to really any particle in a bound system. Whether we've probably heard of particle in a box, which is just a particle moving in a confined region of space, and it also certainly applies to an electron in an atom, which is a bound particle around the nucleus. So you apply this equation. Let's try to first understand what some of these terms mean before we talk about the physical description of them. And we're not going to make you responsible for you should understand the Schrodinger equation, what it is, and sort of what it means. But obviously, we're not going to be solving the Schrodinger equation in this class. Because the reality is the mathematics behind this requires a knowledge of math that probably is at least calculus 2 or above, and we don't expect you to know that for this course. But what these terms mean, H here is called a Hamiltonian. So this Hamiltonian is not simply a number or a term, it's really a series of mathematical operations. And so you take these mathematical operations and you apply them to this, what's called the wave function psi, which we'll define in a second, or define in a second. And so when you apply these set of mathematical functions to the wave function, you're going to yield one of the allowed energy states. Okay, so what we're really interested in, which allows us to predict a lot of properties of atoms and allows us to talk about their chemical reactions that they undergo. We want to know the energy states of the electrons. What are the energy levels that the electrons reside at? And this Schrodinger equation allows you to do it. So you apply this Hamiltonian to the wave function and you return the energy of that wave function multiplied by the wave function. And then that's what this psi is. We call it a wave function. So we talked about in our introduction to quantum mechanics this wave-particle duality, where there's not really a separate category of waves and particles. Everything has both wave and particle behavior, and this wave function sort of accounts for that idea with the electron. So the electron is not simply a particle moving in a circular orbit, but is better described as in a wave equation. So it describes an electron as a standing wave, not as a particle moving in a circular orbit as the Bohr model did. So this really brings out that wave nature of electrons. And the function is parameterized in terms of x, y, and z coordinates, so it's a three-dimensional function. Although in reality we usually think of it more in spherical coordinates, where you just have the nucleus at the center and then some distance r from the center. But you can think of it as x, y, and z as well. It depends on how you write the equation. Now the important point about a wave function, and the point that we really need to start to understand as we derive this more complicated model, is that this does not tell us the exact position of the electron. All right, so we want to get away from the idea that we have these regularly defined orbits where we know exactly where the electron is around the nucleus. That's just simply not the case in reality. So this wave function does not tell us the exact position of the electron. And then each energy level in the atom, so we're going to talk about the different energy levels in atoms, has its own associated wave function. So for every, for the ground state, it's going to have its own wave function. For any excited state, which is a higher energy state, you're going to have a separate wave function that describes all of those. But the point is, the wave function, when you're talking about the electron's position, does not give you an exact position. And the reason for this, which is another early idea of quantum mechanics, is the idea of the Heisenberg uncertainty principle. So, the Bohr model sort of predicts that you can know exactly where the electron is in space and that it's moving in a regular circle, but the Heisenberg uncertainty principle sort of says that's not the case. So we're not going to be responsible for really using this equation on any homework problems as far as I know, but it looks like this. So delta x times delta m times v is greater than or equal to h over 4 pi. All right, so delta x is the uncertainty in position. So that's basically how closely can we really know where the electron is? To what precision can we know the location? Can I say that it's right here, or is it actually in a region? Is it actually a larger region that's uncertain? M is the mass of the electron, or whatever particle we're talking about, and then delta v is the uncertainty and the speed. All right, so we have an electron orbiting the nucleus. This equation tells us how precisely, depending on how fast it's moving, how precisely can we know exactly where that electron is? Is it possible to narrow it down to a very specific point, or is it really a more uncertain arrangement? And so what it tells us in basic forms is that it is impossible to simultaneously know the position and momentum or energy of a particle. There's an equivalent form of this equation that deals with kinetic energy as well. So you can think of it in either term, momentum or energy of a particle. And just like we saw for a lot of the ideas of wave-particle duality, we talked about the de Broglie wavelength, where you can calculate the wavelength of any particle. This really only matters for very small particles or very small objects. All right, so going back to the baseball analogy that I had before, if I was throwing a baseball, across the room, however fast I'm able to throw it at my advanced age, so if I was throwing a baseball through the room, and we were to use the Heisenberg uncertainty principle to calculate the uncertainty in the position, we can do simple physics calculations to say if I throw the baseball this fast to the back of the room, at this time it's going to be here, at this time it's going to be there, and so on. What's the uncertainty in our ability to calculate that? Well, that's going to be excruciatingly tiny compared to the size of a baseball. So we can calculate the uncertainty in position, and it's going to be, 10 to the minus 20-something meters, which, compared to the size of a baseball is nothing. So for really large objects, Heisenberg uncertainty doesn't matter at all because the uncertainty is so tiny compared to the size of the object. But what happens if we're talking about electrons? Let's do a quick calculation. Like I said, I don't think you'll have to do these calculations on the homework assignments or tests, but just to get an idea of how this equation works. So let's say we measure the speed of an electron to be 1.0 plus and minus 0.1 times 10 to the 6 meters per second. So if you're not used to dealing with uncertainties, you'll certainly encounter them in the laboratory. This basically means this electron is moving somewhere between 0.9 and 1.1 times 10 to the 6 meters per second. That's the best that we can measure it. Okay? And we want to know what is the uncertainty in this position. We're giving you the mass of the electron here in kilograms, which is the relevant unit for this type of calculation. So let's see what this is. This is a reasonable speed for an electron. It sounds like a very fast speed, but electrons certainly do move this speed quite often in real situations. So we're going to calculate the uncertainty in position. Delta x times m delta v has to be greater than or equal to h over 4 pi. All right, so we have the mass here of the electron, and then the uncertainty and velocity delta v is given to us as this plus and minus 0.1 times 10 to the 6. So that's the uncertainty and the speed. That's the the sort of fudge factor, the range of the speeds that we don't really know exactly. So our delta v is plus and minus 0.1 times 10 to the 6 meters per second, which we don't really need to consider both the plus and minus part of it. It's just 1 times 10 to the 5th. All right, so we know the speed of this electron to somewhere within 1 times 10 to the 5th meters per second. And so we just plug the numbers in. Delta x is greater than h over 4 pi times m delta v. So h, remember, is this constant that we talked about a lot the last few lectures. 6.626 times 10 to the 34th joule seconds. Now you can probably tell because the numerator of our fraction is so small, it really only matters for small objects. And so if we put the mass and the velocity of this electron down here, 4 pi, and then the mass is 9.11 times 10 to the minus 31st, and the uncertainty and the speed is 1 times 10 to the 5th, we calculate an uncertainty in position of 5.8 times 10 to the minus 10 meters, which is 0.58 nanometers. Now that may not sound like a very big uncertainty to you, 0.58 nanometers is really, really tiny in reality, but if we compare it to the size of a hydrogen atom, this is 10 times larger than the hydrogen atom. Okay, so hopefully this little sample calculation, which doesn't necessarily have a lot of basis in reality, but it shows you if we have an electron moving at a reasonable speed around the nucleus, we have no idea relative to the atomic scale where that electron actually is. So compared to the size of an atom, the uncertainty in an electron's position is huge. So this drives home the point, hopefully, that we can't just use simple circular orbits to describe an electron. We have to use wave functions, which are probabilistic models of where the electron may be, but doesn't tell us exactly where it is. So that wave function psi, this is the reason why we have to use something like the Schrodinger Equation, because we can't know exactly where the electron is when we're talking about the size of an atom. Okay, so compared to the size of an atom, our uncertainty in position is very large. So that's why we're forced to use this Schrodinger equation and these things called wave functions to describe the position of an electron and its energy and all those things that we're interested in. So what we're going to talk about in terms of wave functions, we're not going to give you the mathematical equations for them because, like I said, they're very complicated. And if you just look at them, it looks like a bunch of Greek letters and alphanumeric soup. That doesn't say a whole lot to us. But what we want to know is what's really the physical interpretation of a wave function, this equation psi, this thing that we talked about in relation to the Schrodinger equation. And so we're going to use some definitions first, and we're going to talk about really what does psi mean in a physical sense, not really get into the mathematical details of it. If you take physical chemistry down the road, you'll certainly see a lot more of the mathematical details of wave functions if you're interested in that. But for now, we're just going to worry about the physical interpretation of what they mean. So the word that we're going to use more often than wave function is orbital, but in a lot of senses, this is a synonym for a wave function. And so this orbital or wave function, what the physical significance of it is it allows us to determine the probability of finding an electron in a certain region. Okay, so the Heisenberg uncertainty principle says we can't know exactly where the electron is, but we can certainly define a probability of finding it in a certain place. And that's what the wave function or the orbital tells us. All right. So then the two things we're going to talk about in relation to this are what are called probability density and radial probability density. These are both related to the wave function, but they give us some idea about the probability of finding an electron near the nucleus or in some region outside the nucleus. So probability density is given by psi squared. So if we square the wave function, that gives us the probability density. And it's really simply all that it is the probability of finding an electron at a given point in space. All right, so as I said, the wave function can be parameterized in terms of x, y, and z. You pick some random value of x, y, and z, plug it into the wave function, square it, and that gives you the probability of finding an electron at that exact point in space. This is not the most useful parameter, as it turns out, so we'll talk about it a little bit, but the one that's more important is radial probability density, because we think of atoms as being spherical objects, so what we're really more interested in is what's the probability of finding it at a certain distance from the nucleus, not just at any random given point in space. And so that's what the radial probability density gives us. If we take that probability density psi squared and multiply it by 4 pi r squared, that gives us what's called the radial probability density, which is the probability of finding an electron at that radius. And so that r is the radius that we're interested in, and it's just the probability of finding that electron at a certain distance r from the nucleus. All right, and that's often what we're more interested in, is the radial probability density, which tells us something about the size of the atom, how far away the electron is, and as we'll see, is also related to the energy. Okay, so those are how we really want to interpret wave functions. We don't want to think about the mathematical details. We want to just interpret them as being probabilities that we can relate to either the absolute probability at a certain place or the radial probability. So let's look at some plots that kind of describe the difference between radial probability and normal probability distribution. So if we think about the probability distribution for an electron, we're going to talk about the ground state hydrogen atom first, but although this more or less applies to many other atoms as well in a qualitative sense. So this first graph, I'm going to show you what the probability density looks like. So if we take the wave function psi and we square it, and then we plot that as a function of the distance from the nucleus, what it looks like is just a monotonically decreasing function. And it never quite, so it decreases with radius and it never quite gets to zero. So in these probabilistic models, specifically for the hydrogen atom, there's never a zero probability of finding the electron somewhere. So it may sound weird to think about that. If I put a hydrogen atom at the center of the room, there is a non-zero probability that its electron could be up in that corner of the room. Now, it's obviously an excruciatingly small probability of that actually being there, but this probability density never quite gets to zero. Well, the part that might be a little bit weird for us is, well, the probability density goes up and up and up as we get closer to the nucleus, so why doesn't the electron just sit at the nucleus the whole time? And that's because, remember, that this is just the probability of finding an electron at a given point in space. But as you move away from the nucleus, there's more and more points in space at a given radius. So in other words, think of if you took a hydrogen atom and you blew it up to the size of this room, and then you divided that hydrogen atom into spheres that are increasingly bigger and bigger and bigger and bigger, little shells that you divide it up into. And at the first shell, you have a very high probability density, but you have a very small volume, a very small region of space where the electron can be. And as you move farther and farther away, the probability density at a given point goes down, but there's more points at that volume, at that distance from the radius. So there's kind of two competing things here. As you go away from the nucleus, the probability gets smaller. So that's what this plot is showing here, where the color is getting lighter and lighter. But at each point further and further away, there's more points where the electron can actually exist at that radius. So you have kind of one function that's decreasing with radius, one function that's increasing with radius, which is the volume element. And so what you really get when you look at radial probability distribution, and this is the one that's more important and we're going to talk about almost exclusively, is a plot that looks like this. So when we talk about the radial probability distribution, you have some maximum here before it decreases and decreases. And again, I should draw this a little bit better. It never quite gets to zero. So the radial probability distribution also never goes to zero. So it's an asymptote. And so when you look at radial probability distribution, you do have some radius where the electron is most likely to be found, even though the probability density is not necessarily highest there, but there's that's the region in space where it's most likely to be found. So this peak here is what we call the most probable radius. Which is for a hydrogen atom 0.529 angstroms. Now that's not a number you have to memorize, but the significance of that is this is the exact radius that Bohr predicted. So the Bohr model predicted that the electron will be orbiting at that exact radius, and the quantum mechanical model says that this is the most probable radius. So there is some consistency there. The Bohr model, it predicted a radius that is in fact the most probable place to find an electron. But this quantum mechanical model says that there's also a probability of finding an electron at a lot of other places too. It's not just a single defined circular orbit. And now when we're talking about an orbital, what we tend to do is we'll define what's called a 90% probability region. So obviously, as I said, the electron can, in reality, could exist anywhere. There's nowhere where the probability is exactly zero in the case of a hydrogen ground state. But what we're really interested in is where is the electron most of the time. So we'll define some region of space, this area under the curve here, that accounts for 90% of the total probability. And that's typically how we define our orbitals here. So this is what we call the 90% probability region. So when we draw pictures of orbitals, as we're going to start doing very soon, which is sort of a picture of the region of space where the electron is most likely to be found, we're going to typically think of it as the 90% probability region is how it's done in standard. So for a hydrogen atom, what this 90% probability region looks like is a sphere. All right, so for the hydrogen atom ground state, you can draw a sphere, which is the region in space where the electron is going to be found 90% of the time. But you cannot say with any certainty where it's going to be at any given time. Okay, so it's a region in space where it could exist, but it's in reality existing at all of those places simultaneously. All right, so to understand now orbitals in more detail and to talk about these wave functions more specifically, we have to define what are called quantum numbers. And so like I said, we're not going to do the full mathematical equations of wave functions, but we do want to understand some parts of them which are called quantum numbers. So when you write out equations for wave functions, you have a set of parameters that are called quantum numbers that will tell you certain things about that wave function, and that's what we want to understand in this course. So quantum numbers are a series of integers, typically, at least for orbitals, There's one other quantum number we'll talk about next time that's non-integer, but they're all simple numbers. And these integers are some parameter, some part of the wave function, if we were to write out the full equation. And by knowing what these quantum numbers are for a certain electron in an atom, you can describe the energy, shape, and orientation of the orbital. So we're going to just start by talking about orbitals for now, which is regions where electrons can exist. We'll talk about the individual electrons next time. Okay, but if you know the quantum numbers, this series of integers here, you can define the energy, the shape, and the orientation of the orbital, which is the region in space where the electron is going to exist for that particular orbital. So we talked about quantum numbers a little bit for the Bohr model. We said that there's that one quantum number n, which describes the distance of the electron from the nucleus and also is related to the energy of the electron at that position. And so that quantum number still exists for multi-electron atoms and for the quantum mechanical model that we're developing now. And just like before, the allowed values of n are 1, 2, 3, 4, so on. So any integer value starting with 1 is the first quantum number. So we call this the principal quantum number. It's the first one as we typically define these. And then what does it tell us physically? It tells us the energy and the size of the orbital. And another synonym for this is what's called the shell number. So we're talking about in an atom, the first shell is where n equals 1, the second shell is n equals 2, and so on. And so this first quantum number, just like it does for the Bohr model, it tells us the size of the orbital. Remember, in the Bohr model, the quantum number n tells you how far away from the nucleus you were. And just like it does in the Bohr model, it's related to the energy of that orbital as well, the energy of the electron that would be in that orbital. The second quantum number is L. We typically write it as a cursive L. And all the quantum numbers, their values depend on each other. So n can be any number 1, 2, 3, and 4. And then depending on what your value of n is, you're going to have certain allowed values of L within that shell. So L can be anything from 0. So the smallest value of L is 0. And then the largest value of L is n minus 1. So depending on what your value of n is, what shell you're in, that's going to define which values of L you can also have. So it's just from 0 to n minus 1. Okay, so if n equals 1, L has to be only 0. If n equals 2, L can be 0 and 1, and so on. Now what exactly does this tell us? The quantum mechanical descriptor of this is the angular momentum quantum number. So it tells us something about the angular momentum of the electron in that orbital. But of course that's not a very important thing to think about for a chemist, but what it really tells us that is important is the shape of the orbital. So we said that the orbital that describes the hydrogen ground state is spherical, but not all orbitals are spherical, as we'll see. So the orbitals can have different shapes, which is again the region in space where the electron can be. It does not necessarily have to be a sphere for every different value of L. And it also does contribute to the overall energy of the orbital as well. Now this is something you're going to have to remember because it's going to come up on homework questions. L only helps determine the energy when there's more than one electron. If you have a one-electron atom, like a hydrogen or some ion that only has one electron, just like we saw for the Bohr model, you only need the value of n to tell you the energy. But if you have more than one electron in an atom, then you have to use n and L to determine the energy of that electron. It'll depend on both of those quantum numbers, not just one. And then the third quantum number that defines an orbital is m sub L. So it's m with the subscript L. And the values of m sub L depend on the value of L that you're talking about. So it goes from minus L to plus L. So this is the only one that can have negative values. And it also includes 0. Alright, so it's minus L to plus L including 0. So if L equals 1, it'd be minus 1, 0, plus 1. And we'll see a lot of examples of that going on in the future. This is called the magnetic quantum number. enlarge that by accident. Alright, so this m sub L is the magnetic quantum number. And what it tells us is the orientation of the orbital. Alright, so for orbitals that are not spherical, it can be pointing in this direction or that direction, and that's what m sub L relates to. It also, we're not going to talk about this situation in this course, but it's called the magnetic quantum number because if you put the atom into a magnetic field, this will also contribute to the overall energy of that orbital, but only in that situation. In regular situations, the energy has nothing to do with m sub L. So those are the three quantum numbers. We want to know the relationship between them, but then also, again, more about what they tell us about the orbitals that we're interested in. So another important point to talk about are what are called sublevels. So we talked about n being the shell number, and then if you have a sublevel or a subshell, that's going to be n and L together. Okay, so n is the shell, and then n and L together tells you what's called the subshell or the sublevel. And we want to, get used to the terminology here, because if we're going to, become proficient at chemistry, we need to learn how to speak the language of chemistry. So when you have different values of L, we don't usually refer to them by their numerical value. We give them letter designations that we use instead in a common sense. So the values of L, as I said, can be 0, 1, 2, 3, 4, and so on. Go up to 5 as high as we're going to go. And then all of these values of L refer to a letter designation. So if L equals 0, you're talking about an S subshell or an S orbital in that subshell. If L equals 1, that's a P subshell or P orbital. If L equals 2, that's a D subshell. L equals 3 is F. So you're going to have to remember this order, SPDF, for L equals 0, 1, 2, 3. And then beyond there, it's alphabetical, though we're not really going to see those very much. So you have G subshells and H and so on. But the only ones that we really have to worry about in chemistry are these first four here. These are the ones that are going to occur in atomic ground states. So when we're defining the quantum numbers and the subshells and the orbitals for real atoms, we only have to worry about S, P, D, and F. We don't have to talk about anything higher than that. But that's just the terminology we use. So if you see an S orbital or an S subshell, that tells you that L equals 0. If you see a P, that means L equals 1, D, L equals 2, F, L equals 3. So when you hear those designations, it's referring to that second quantum number, L. Okay, so with that in mind, let's now talk about what's called the quantum number hierarchy. And as I said, all of these quantum numbers depend on each other. So for a certain value of n, you're going to have certain allowed values of L. And then for a certain value of L, you're going to have certain allowed values of m sub L. And so we want to understand the relationship between the quantum numbers and what are the values that we can possibly have. All right, so let's just do 3 of them. So if n equals 1, that's the smallest value of n. And then the value of L has to be from 0 to n minus 1. So that means for n equals 1, the only allowed value of L is 0. Okay, because 0 is the smallest value of L, and then n minus 1, which would be also 0, is the highest value of L. So when n equals 1, this is the only allowed value of L, is 0. And then m sub L is going to be minus L to plus L, as we define. And so if L equals 0, minus L is 0, plus L is 0, and again, you only have one value of m sub L. Alright, so each of these are the allowed values when n equals 1. Now if n is 2 instead, so if we go to the second shell of an atom, or the second level, n equals 2, now our values of L, we have two possibilities. So the smallest value is still 0, but then we also have n minus 1, so 2 minus 1 is 1, so we have the allowed value that is also 1. So for n equals 2, we have two values of L, 0 and 1. And then again, when L equals 0, the only value of m sub L is 0. And then when L equals 1, we have now 3 possible values of M sub L. So M sub L goes from minus L to plus L, so it goes from minus 1 to 1, and then it includes 0 as well. Okay, so when you have n equals 2, you have a lot more possibilities. You have L equal to 0 or 1, and then when L equals 1, you have 3 allowed values of M sub L, minus 1, 0, and plus 1. We'll do it one more for n equals 3. So the allowed values of L for n equals 3 are going to be, starts at 0 and goes up to n minus 1. So the largest value is 2, and it's every value in between, so 0, 1, and 2. So it's all inclusive values that fall into there. When L equals 0, as you've already seen, the allowed values of M sub L are 0. When L equals 1, the allowed values of M sub L are minus 1, 0, and plus 1. And then when L equals 2, I'm going to have to push this over a little bit more to fit it. The allowed values of M sub L, we have 5 of them. So the smallest one is minus L, which is minus 2, minus 1, 0, 1, and plus 2. So all values going from minus L to plus L. So when L equals 2, you go from minus 2 to plus 2, and all values in between. So this is how the quantum numbers depend on each other. So depending on which value of n you have different allowed values of L, and depending on which value of L you have different allowed values of M sub L. And then when we're talking about what we define as an orbital is any set of 3 quantum numbers. So if you're in the n equals 3 shell, 3, 0, 0 is one of your orbitals. 3, 1, minus 1 is another orbital. So any set of 3 quantum numbers that are allowed, that are compatible with each other, is defining a single orbital in that atom. So in n equals 3, 3, 2, 2 is another orbital, and so on. So if you look at your total number of allowed values of M sub L, that's going to tell you how many orbitals are in a given shell or subshell. So in the n equals 3 shell, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 different values of M sub L that are allowed, which means you have 9 total orbitals in the n equals 3 shell. So there's some simple relationships that we can derive then for doing that. So as an example, how many orbitals are in the third shell? I just gave this to you by accident. I wasn't meaning to do that. But as I said, an orbital is defined by an n, L, and M sub L set. So if we have a set of 3 quantum numbers, where again they have to be an allowed set of 3 quantum numbers, where we follow the rules that I gave you for how those numbers depend on each other, that defines a single orbital. So if we have a given value of n, the number of orbitals in that shell is given by n squared. So for n equals 1, there's 1 orbital. For n equals 2, there's 2 squared, which is 4 orbitals. For n equals 3, there's 3 squared, which is 9 orbitals. For n equals 4, there's 4 squared, which is 16 orbitals. So if you know the value of n that you're interested in, you can figure out how many orbitals are in that shell. And then if you're talking about a given subshell where you have a value of L, and you want to know how many orbitals are in that subshell, the number of orbitals is 2L plus 1. Okay? And that's because there are 2L plus 1 allowed values of M sub L for a given value of L. Okay, so if you know N or L, you can figure out the number of orbitals that are either in the shell, which is given by N, or the subshell, which is given by N and L together. Okay, so if we're in the third shell, as this example problem gives us, and as I unintentionally let the cat out of the bag on the last slide, the third shell has 9 orbitals. N squared is 9. And then if we want to know how are these 9 orbitals divided up into subshells, we have in the third shell we have the 3s subshell. That's where L equals 0. There's going to be 2L plus 1 orbitals in that subshell, so that's going to have 1 orbital. We have the 3p subshell. That's the subshell where L equals 1. So if we go back to this slide, when n equals 3, L can be equal to 0, 1, or 2. So when L equals 1, that's the 3p subshell. And then there's 2L plus 1, which is 3 orbitals. L is... And then when we have 3d, which is the L equals 2 subshell, 2L plus 1, 2 times 2 plus 1 is 5. Alright, so this tells you how the orbitals are divided into subshells. So the third shell has a total of 9 orbitals. One of those is in a 3s subshell, or we call a 3s orbital. 3 of those are 3p orbitals, and then 5 of those are 3d orbitals. 1 plus 3 plus 5 is 9. So 9 total orbitals divided up in this way into subshells. Alright, so see a lot of problems on the next homework dealing with that, where you're given a value of n or a value of L and have to determine how many orbitals would have that specific quantum number. Alright, so let's do one more example. How many f orbitals are present in a given f subshell? Alright, so for this we need to know the value of what the value of L is. And very often, as I said, for L we don't give you the number, we give you this letter designation. So we just have to remember these 4 primarily. S, P, D, and F. So we're talking about an F sublevel, so that means L equals 3. And as I just gave you on the last slide, the number of orbitals is 2L plus 1. 2 times 3 plus 1 is 7. Okay? So whenever you're in an F subshell, whether it's 4F, 5F, 6F, within that subshell there are going to be 7 total orbitals. Okay? Okay, so that's how some of those relationships work. And you'll see a lot of those on the homework, as I said. Now let's move on now to talk a little bit more in detail about the shapes of these atomic orbitals. So we have to understand the relationship between the quantum numbers, and now let's talk about physically what they mean in more detail. Alright, so first some key terms that are going to help us understand the shapes of orbitals. So, as I mentioned, these are all determined from wave functions, which are mathematical equations. And a node is a place where the wave function goes to 0, or more specifically where the probability distribution, the psi squared, the wave function squared, goes to 0. So a node is a region where the electron has 0 probability of existing. Okay, for the hydrogen ground state, we didn't see that. Did I post the wrong notes? I see a lot of confused glances in the audience. I made some changes last week and apparently forgot to update them on Blackboard. I apologize for that. So I will post the corrected blank and I'll post this as well. So try to follow along as best you can. There's only 2 more slides left. And then I'll have everything posted on Blackboard that you can certainly take a look at when I'm done. So I'm sorry about that. Alright, so then the radial node, unless, well, it's possible if you downloaded them too early, if you were really excited about getting these lecture notes and did them too early, I may have changed them after you downloaded them, but I may have also forgotten to change them, so I will check on that when I get back. But anyway, let's continue on and finish this off and follow along as best as you can. So a node is a region where the electron has 0 probability of existing. We didn't see that for the hydrogen ground state, but for many orbitals this is a case. You have some place where the electron can exist. And there are 2 kinds of nodes we want to be worried about, or want to learn about. So a radial node is, as the name implies, it's a radius where the electron cannot exist. So the electron has 0 probability of existing at that radius. Alright, so that would be you go to some distance from the nucleus r, and at that distance there's 0 probability of finding an electron there. And so you can easily calculate the number of radial nodes. There's a simple relationship here. So the number of radial nodes is determined by the subshell that you're in. It's going to be n minus L minus 1. Okay, so for a given subshell, which is a pair of n and L values together, the number of radial nodes is n minus L minus 1. Alright, and then the nodal plane is a 2-dimensional plane where the electron has 0 probability of existing. And as we'll see when we start drawing these next time, this nodal plane, or how many nodal planes you have, is going to determine the overall shape of the orbital. All right, and when I introduced the quantum numbers a few slides ago, I said that the second quantum number L is related to the shape of the orbital, which is then, of course, as I just said, related to the number of nodal planes. And so there's a very simple relationship here. The number of nodal planes equals L. So for L equals 0, you have 0 nodal planes, which, as we saw, gives a spherical shape, and we'll talk about that more next time. When L equals 1, you have 1 nodal plane. When L equals 2, you have 2 nodal planes, and those are going to give different distinct shapes for that orbital depending on the value of L. All right, so let's just talk, the last thing we'll talk about are the very simple ones, the s orbitals, and we'll talk about their shape a little bit. So when you have an s orbital, L equals 0, and these are going to be spherical in shape, which means they have no nodal planes. Okay, so when L equals 0, you have 0 nodal planes, which means you get a spherical orbital shape, or what we sometimes call electron density. So let's look at the difference then between different shells, 1s, 2s, and 3s. So we know we can have, for L equals 0, that can occur in any of the shells, 1, 2, 3, and so on. So if we have a 1s orbital, it's going to be spherical in shape, but let's look at what the radial probability distribution looks like. And this is pretty much what I showed you for the hydrogen atom. So the radial probability distribution for a 1s orbital is going to look like this, and this has 0 radial nodes as well. All right, so we want to also understand what these radial nodes tell us. So for a 1s orbital, n minus L minus 1 is 0, there are 0 radial nodes. For a 2s orbital, where n equals 2 and L equals 0 still, we have n is 2, so 2 minus 0 minus 1 is 1 radial node. So for 2s orbital, we have 1 radial node, and the shape looks like this. You have a little maximum here, you have a place where it goes to 0, and then you have another maximum farther out. Okay? And this is your 1 radial node right here. This spot where the wave function, or the probability distribution more specifically, goes to 0, where it touches the x-axis. Now, one of the great mysteries in life is, well, how does an electron go from a place over here that has non-zero probability to a place over here that has non-zero probability while crossing over a place that has no probability? How is that even possible? That's called tunneling, and that's one of the great mysteries of life as far as I can tell. I mean, it's a quantum mechanical thing. That's how people always explain things and don't understand them. Oh, it's quantum mechanics. But, there's this place here where the electron cannot exist at this distance, but yet somehow it can exist here and it can exist here. That's kind of a far out confusing thing to think about. So the shape of this orbital will look very similar. You'd have your nucleus here, but you'd have a spherical electron density, but you'd have some place where the electron cannot exist, that node there. It's a terrible sphere. I'm going to try it again. So you'd have your nucleus in the center. You'd have an overall spherical electron density, but then you'd have some radius where the electron cannot exist. But it still looks like a sphere. It almost looks like 2 concentric spheres. There's just some value of r where there's 0 probability of finding the electron. And then for a 3s orbital, to close things out today, n equals 3, L equals 0, so now we have 2 radial nodes, n minus L minus 1 is 2, and then we get a distribution that looks like this. Now we have 2 places where the wave function, or the probability distribution, goes to 0, and then it looks something like this. So now our 2 radial nodes, we have 1 there and 1 there. So now we have 2 places, 2 radii, where the electron cannot exist. Okay, so these are the shapes of s orbitals. These are the simple ones because they're spherical, but we should also understand what exactly a radial node tells us. And next time we'll talk about p and d orbitals, which have more complex shapes.